Dear students, welcome back to lecture 2 of our scaling section of software architecture and design course. And in this lecture, we are going to talk about read replicas and write scaling, right? Before you resort to sharding, which we covered in our previous lecture, there's a much simpler scaling technique available to you, and that is read replicas, right? So most web applications are read heavy, and a typical ratio is 80 to 90% reads and 10 to 20% writes. So if you are overloading your database, the bottleneck is almost always reads. So we need read replicas, and which let you add capacity for reads without any application sharding, right? Without changing your query logic, and with minimal operational overhead. So this lecture also covers write scaling strategies, like what to do when writes themselves become the bottleneck. So let's start with the fundamentals. Dear students, now let me explain the fundamental insight behind read replicas, right? As you know that most web applications are dramatically read heavy. If we talk about an e-commerce store, so when a user search for a product, so that is read. And if we talk about the social media, so when a user loads their social media feed, so that is read. And when a user view the dashboard, so again that is read. And when they check their balances using mobile banking application, so again that is read operations. So writes only happen when they post something like add to cart or make a purchase. So only in that case write happens, right? And the typical ratio is 80 to 90% reads and 10 to 20% writes. And for analytic heavy applications, it's closer to 99%, right? So this imbalance is actually good news, because it means most of your database load is on the cheapest kind of operation to scale. And think about it like reads do not need to be on the primary database. They do not need to be strongly consistent. They just need to return accurate enough data quickly. And this opens up a whole set of scaling strategies. So before you reach for sharding, which adds enormous complexity, you should always ask, have I already used every possible method to handle more read requests? In many cases, the answer is no. So read replicas can multiply your read capacity many times over the minimal complexity. So let's see how they work, right? Dear students, here's how read replicas work. So you have one primary database that accepts all writes, and it is the source of truth. And each insert, update, delete operation goes here to this primary database. And when any of such operations happen, so the primary database records that operation in its WAL file. WAL stands for write ahead log, right? It is a kind of file where each type of write operation history is stored, and then all the replicas are continuously streaming that WAL from the primary database, and they replay those changes on their own copy of the data. So this typically takes less than 100 milliseconds, which means that the replicas are almost always current, right? So now you know that your read traffic, which is 80 to 90% of your load, so you can go to any of the replicas instead of the primary database, right? And you have essentially divided your read load by the number of replicas. So if you have 3 replicas, now your read capacity will be 4 times because you have one primary plus 3 replicas. And if you have 5 replicas, so in that case you will increase your read capacity to 6 times. So this is huge. You went from one server handling everything to 6 times read capacity with relatively little complexity, right? So the replicas are always slightly behind the primary a database, like if a user posts a comment and immediately refreshes the page, so they might not see their own comment for a fraction of a second, but this is usually acceptable for social features and dashboards and search, but it's not acceptable for financial transactions or inventory management, where you need strong consistency. So the pattern for most application is that use primary for writes and reads that need strong consistency, and you can use replicas for everything else. Dear students, once you have maxed out your read scaling with replicas, writes can still be a bottleneck, and here are 4 strategies which you can apply, and you can scale your writes. So the first strategy that we have is a write ahead log batching, right? By default, PostgreSQL flushes every transaction to disk synchronously, and this is safe but slow. So you can trade some durability for speed by enabling asynchronous commits, which batches writes and flushes in groups. So you might lose up to 100 milliseconds of data in a crash, but you can get 5 to 10 times write throughput. And for analytics events or non-financial data, this is often acceptable. And the second strategy that we have is connection pooling, right? And this one surprises a lot of engineers. PostgreSQL creates new OS process for each connection, and with 10,000 concurrent F instances, you would need 10,000 database connections, and each consumes approximately 10 MB RAM, right? So that's 100 GB, and it is used just for idle connections, right? So tools like PgBouncer can be used, and PgBouncer sit in front of the database and multiplex thousands of application connections over a small pool of real connections, let's say 100 or 200. So this dramatically reduces memory pressure and allows you to handle far more concurrent users. Then the third strategy that we have is write queues, right? And for non-critical writes, like recording that a user viewed a product or logging a page view, so you do not need to write synchronously in the request path, right? So publish to Kafka or SQS, return success to the user immediately, and let a background worker batch insert into the database. So this decouples your write throughput from your database real-time write capacity. Then the fourth strategy that we have is vertical scaling. Before sharding, always consider just buying a bigger machine. Cloud providers offer instances with 192 vCPUs and 1.5 TB RAM. If you are spending 20,000 a month on application servers, so spending on an extra 5,000 on a more powerful database instance might be the cheapest path forward. So simpler is always better when it works. Dear students, once you create read replicas and you want to divide the read load among the replicas. Now the next question is that how the load is divided among the replicas. So routing reads to replicas sounds simple, but there are subtle patterns to know about, and we are going to talk about each of those patterns. The first one is round robin pattern. And this is the simplest approach. Your load balancer rotates queries across all replicas, and it works great most of the time. But the problem with this pattern is that a user posts a comment and then immediately refreshes the page. So the read goes to a replica that is 200 milliseconds behind, and they do not see their own comment. So this feels like a bug to users, right? So this is the main problem with round robin. And the next pattern that we have is sticky session routing. And it routes all reads for a given user to the same replica. This reduces the chance of seeing stale data, but it means your most active users always hit the same replica, and potentially can create hot spots. Then we have a next pattern, that is read your writes, right? And after any write from a user, the next few reads from that same session go to the primary database, and this eliminates the problem in which the user say I can't see my own post, right? But it increases primary load slightly, and it is usually worth it for user facing write operations. And then the fourth pattern that we have is lag aware routing. You can monitor the replication lag of each replica in real time, and if a replica is lagging by more than let's say 500 millisecond, so stop routing it until it catches up. And this requires more infrastructure but gives you dynamic fallback behavior. So my practical recommendation is that you can start with round robin for most traffic, and read your writes for any user facing writes, and then read operations like post a comment, upload a photo, place an order, right? And then you can skip lag aware routing unless you start seeing user complaints about stale data. And most ORMs and database libraries have built-in support for primary replica routing, right? So like Rails has a native multi-database configuration, and similarly Django supports database routers, so you rarely need to build this by yourself. Dear students, now let's take a look at how you can physically arrange your replicas around your primary database. And there exist two strategies for arranging your replicas around your primary database. The first one is a single primary plus multiple replicas, and this is the standard setup most commonly used, right? Where we have one primary database, and different replicas are connected directly to the primary database, and one primary streams wall to all replicas directly. Wall means write ahead log, which is used by all replicas directly, and that wall is maintained by this primary database, right? So each replica independently replicates from the primary database. It is simple and easy to manage, and it works well up to about 5 to 10 replicas before the primary starts spending significant CPU streaming to all of them. And then the second strategy that we have is cascading replication. When you need more replicas, let's say we have 20 plus replicas where the primary would be overwhelmed streaming to all of them. So instead you create a tree, and the primary streams only to 2 and 3, which are the intermediate replicas, and those intermediate replicas stream to leaf replicas. And here you can see the primary only handle 2 and 3 application connections, and this is how very large streams scale their read capacity nearly infinitely, right? But here is the trade-off with cascading. Leaf nodes are further from the primary in the replication chain, right? So their lag is slightly higher. Replica 3 and replica 4 in this diagram lag behind the primary by the sum of 2 application steps. So usually still under 1 second, but worth monitoring. And cloud databases services like Amazon RDS and Google Cloud SQL handle much of this complexity for you. You can add read replicas through a UI click, and they manage the wall streaming, monitoring, and failover automatically. Dear students, read replicas are not just for scaling, they are also your path to high availability. And when your primary database goes down, you need to promote one of the replicas to become the new primary, and this is what we call failover, right? And the failover process includes some steps like first we detect whether the primary database is down or not, and then if it is down, so then we have to choose which replica to promote, and then we promote that replica to primary, and then we update the DNS or connection strings so apps connect to the new primary, and reconfigure remaining replicas to replicate from the new primary. So these are some steps in the failover process, right? And the parameters, the key metrics which are used, and this process are, RTO. RTO stands for recovery time objective, which tells us that how long until the system is, writable again. And RPO stands for recovery point objective, which tells us how much data do we lose, right? So manual failure means an engineer does this manually, and it could take 15 to 60 minutes, which is not acceptable for most production systems. And Amazon Web Services RDS multi-AZ uses synchronous replication to a standby, right? And can fail over in 60 to 120 seconds automatically. And then the PRO is near to 0 because every write is synchronously confirmed on the standby before acknowledging to the client. Then tools like Petroni, which is open source tools, and that watch the primary and detect failures and run leaders election among replicas, and then automatically promotes a new primary, and this gets RTO down to 10 to 30 seconds. So my recommendation is for production databases, always use multi-AZ or HA tools like Petroni, and the cost is modest and the peace of mind is invaluable. Dear students, and now let's talk about 5 takeaways from this lecture, right? So number first, reads dominate. If your database is struggling, the first question is, are reads the bottleneck? They almost always are. And adding read replicas is the highest leverage, lowest complexity scaling action available to you. Number 2, replicas are asynchronous, and that's okay. Sub 100 millisecond lag is imperceptible to users for most read operations. Reserve the primary for writes and strongly consistent reads only, and use the read your writes pattern for user facing operations. Number 3, before sharding writes, exhaust your write scaling options. Connection pooling can improve 10 times your connection capacity, right? And write queues decouple write throughput from DB capacity. Vertical scaling often surprises you with how much it helps. Number 4, plan for failure from day 1. Running a production database without HA plan is a disaster waiting to happen, right? So use multi-AZ on RDS or deploy Petroni for self-managed PostgreSQL. Number 5, replicas before sharding. A well-configured primary database with 5 read replicas can handle hundreds of thousands of reads per second. Only reach per sharding when writes themselves are genuinely the bottleneck, right? So that's all for this lecture. See you in my next lecture, in which we are going to talk about the consistent hashing, the algorithm that makes hashing, hash sharding practical at scale. So see you there.
Thank you so much for watching this. Before you go, please don't forget to subscribe to my YouTube channel and turn on the notification bell so you never miss any of my upcoming videos. I regularly share valuable lessons, practical tips, and step-by-step tutorials to help you improve and grow. And if you are serious about mastering software design and architecture and want a complete structured learning experience, so I have created a full course that includes detailed lessons, assignments, quizzes, and downloadable workbooks to help you practice and apply what you learn. So if that sounds helpful, just check the link in the description below and enroll in the course today. I would love to see you inside and support you on your learning journey.